Okay, so it might be useful to actually go through an example of how we would go through and construct a confidence interval. So suppose we sample 25 picas and the average body length is 6.3 inches. It is known that the population standard deviation in the average body lengths is 0.6 inches. And they've asked us to find a 95% confidence interval for the population mean body length of all the picas. Okay, so a couple of pieces of information that we should probably sort of pick out from here. They want a confidence interval for the mean, right? So we have sort of a formula for that. It's this x bar plus or minus z alpha over 2 and then sigma over the square root of n. Okay, in the case where sigma is known. And in this case, it says, you know, the population standard deviation is 0.6. So it is known. So that's our sigma. We're going to plug that in for sigma. Okay, maybe I'll even write that in here. This here is going to be the 0.6. And working off of that, we also need to figure out what n is. That's our sample size. So in this case, it says we're sampling 25 picas. So we're going to plug in 25 here for n. Okay. X bar is our sample mean. Okay. And from our sample, it says here that it's 6.3 inches. So that's what I'm going to plug in here for X bar. Okay. So the only thing left to figure out is this Z alpha over 2. Now, in order to do that, we have to know either the confidence level or the error rate. And they've given us the confidence level. They said it's 95%. So if you're a person who likes to memorize things or look things up on a table, you can go back to the table that I gave you that gave you the confidence level for 95%. It'll tell you exactly what Z alpha over 2 is. Or let's work it through together. It's not that tricky to do. So we know that it's 95% confidence. So that means that 1 minus alpha has to be 95%, which means that alpha is what's left over, 1 minus that. So it's 0.05. We've got a 5% error rate here. Okay. Alpha over 2 in that case would then be 0.025. So if I were to draw this out, here's my standard normal distribution. This area in the right-hand tail is going to be 0.025, and we're looking for this value here. That's going to be my z of alpha over 2. Okay. Now we have a function, Q norm, that we plug into R that will spit out what that critical value is. The tricky part is it likes the area to the right, not the area to the left. So this area to the right, if I wanted to work that out, I know the area under the whole curve is 1. So that area would have to be 1 minus the 0.025, which gives me 0.975. So that's what I'm going to plug in to Q norm. And when I do that, it's going to spit out 1.96. Okay, and we can just check that table I gave you. Here we go. There it is. It is 1.96. So you can just check it and verify. Okay, so that's what I'm going to plug in here for that's what I'm going to plug in here for Z alpha over 2. So this is going to be 1.96. Okay, so if I were to sort of write this out, I'd have 6.3 plus or minus 1.96 times 0.6 over the square root of 25. Okay. Now, quite often, this plus or minus piece will split up into 2 pieces. The minus piece, which gives us our lower bound. So that's going to be 6.3 minus my margin of error, 1.96 times 0.6 over the square root of 25. And then comma, and then I'll put in my upper bound, which is 6.3 plus. So the only difference there is one is the plus and one is the minus sign. Now when I plugged those into my calculator, I got the values 6.065 for my lower bound and 6.535 for my upper bound. Okay. So that's sort of my range of plausible values. So anything in between those two numbers is what I have 95% confidence in. Again, in repeated sampling, I would anticipate that 95% of these intervals I would construct would contain the true population mean mu. Sometimes we'll also say that we're 95% confident the mean is in there. Okay, so that's fine with me too. Okay, so the next question just gets at, well, suppose we wanted to do a 99% confidence interval for the above. And so instead of doing the 95, we're going to do 99. So the question is, we don't actually have to go through and compute it, but is it going to be wider, skinnier, or the same? Nothing else is going to change. X bar, sigma, the square root of n, those things all stay the same. So the only thing that's changing is the z alpha over 2. And maybe let's just go back to our table. So in this case, our z alpha over 2 was 2.57. That's what it was for the 99% confidence. You can go back to the last video to see that if you weren't sure how that happened. So if that number gets bigger, right, that means that this piece here, right, the margin of error is going to get bigger, right, which means that we're going to be subtracting off more and adding more, right, which means that ultimately my interval is going to get wider. So maybe I'll just write that in here. Or maybe I'll just highlight it or something. Wider. That's the right answer. Okay. And this sort of makes sense, right? So if you think about it, if your boss asked you to estimate some mean, right? And they were like, yeah, you know, be kind of maybe, you know, well, your best guess is fine. You're going to give sort of a range of values, right? But if your boss says, give me the mean and it better be, you know, right, like you better make sure the true mean's in there or you're fired, right? Then you're going to be a little bit more cautious and you're going to make the interval be a little bit wider, right? You're going to say, well, just I don't want to lose my job. And so the interval gets wider. The more confident you need to be, the wider the interval gets. Okay. And with that same note, right, if you can be less confident in your answer, the interval can get smaller and more precise.